So hello, everybody. So today I'm going to talk about Rust, obviously, AI and accelerated computing. So let's start with the promise of artificial intelligence. So I think we are at the beginning of a revolution, somewhat similar to the internet revolution. Hopefully, we're not going to go through a crash, but anyways, it's going to change the society. So artificial general intelligence and artificial superhuman intelligence are promised, but I don't think we actually need those for the revolution to happen, since robots are coming, new products are being made, and society is going to get very different. So, well, most computing will be used for AI, since AI is, unfortunately, very computing intensive. So let's go over the current state of accelerated computing. So since artificial intelligence requires so much of compute, you cannot only rely on CPU. So you also need GPUs, TPUs, NPUs, and any other chips. So today, most of AI is actually built with Python and C++. So we have high-level Python libraries like PyTorch that uses low-level C++ libraries like libtorch. And libtorch itself uses QBLAS, CUDNN, and a lot of C++ libraries. Even like CUDA is C++. So yeah, that's the current state of accelerated computing. And unfortunately, it's not perfect, since today you have to choose between two of those three properties. So performance, portability, and flexibility. Unfortunately, you cannot have all of those three right now. So why are those important? Well, first, performance. Since like 2020 or something, we found the scaling laws, and it tells us that if you scale data sets and compute, you get better models. So most of research today is actually on how we can leverage compute and turn it into intelligence. So the more you have performance, the better the models are. And it's kind of similar recently with test-time compute. So you can use model to output marked tokens and reason about things. So we cannot neglect performance. Same thing for flexibility. Most research actually are pretty much an iterative process, so you need to test a lot of different methods. So if you want to find a new neural network architecture, or if you want to find a new optimizer, well, you kind of need to test a bunch of things. And this is possible because of flexible frameworks. Unfortunately, today, portability is a bit lagging behind. So most of research is actually done on NVIDIA's hardware with PyTorch, which is good, but it kind of reduces the availability of shipping models to different hardware. So it's kind of hard to deploy models to mobile phone, and it's a bit more expensive because we have a monopoly. So yeah, I don't think we should neglect portability. Is it only for research? Well, not really, since all of those properties are really useful to build cost-effective prototypes. And neural network is pretty much just code, so any prototype is shipped to production, always. We don't have time to actually rewrite everything. So I think it's important to also have reliable software. So that's why I made Burn. So Burn is a research-friendly, production-ready deep learning framework built in Rust. So the goal of the talk today is actually to convince you that Rust is very good to build production-ready prototypes. So mostly because of fearless refactoring, because of the type system, because of the tooling, it's really easy to iterate over new ideas. So I'm going to show it by talking about how I actually built Burn, so not just AI. But I also want to convince you that Rust is pretty good right now to power AI models. So, oops, OK. I want to start with a video. Yeah, now it works. So this is a demonstration of what you can do with Burn today. So this is a project made by a researcher at DeepMind. It's built with Burn, so this is not Burn, but it's a 3D reconstruction program. So you give 2D images to the model, and it trains on them and generates 3D space. So all of this thing is actually built with Burn. It runs on any hardware, so even in browser because of WebGPU. And yeah, it uses also EGU for the UI. A lot of Rust creates out there, and it's great. So it shows what you can do with AI, not just LLMs, but visual stuff. So it's called Brush. You can go look it out. It's on GitHub. It's open source. So yeah, that's a great project. So I assume not all of you guys are AI researchers or machine learning engineers, so I'm going to define some terms just to make sure everybody understands the presentation. So let's start with the core data structure of AI, which is a tensor. So tensors are multi-dimensional arrays, and if you don't know what it is, it's pretty much a list of matrices. If you don't recall your linear algebra course from university, that's pretty much grid of numbers. So pretty simple, a lot of numbers, gigabytes of numbers sometimes. And neural networks are actually function approximators, parameterized by tensors. So you can see them mostly as objects with tensors as fields. So yeah, and those tensors are actually mutable, and they change during training. That's actually how neural network learns. And since those are functions, well, their inputs and outputs are also tensors. So it's pretty much just a bunch of tensors and tensor operations. And the role of a deep learning framework is to orchestrate all of those things to actually make sense. So now let's go over the beginning of Burn, from the beginning to being actually useful. So this is the old logo. It was just fonts, so it started really as a small project. So I'm going to go over the core architecture of Burn. So this is true from the beginning, because I wanted the deep learning framework to be portable. So I started with the backend trait. So the backend trait is pretty much an abstraction over all of the tensor operations and tensor data structures. I wanted to focus on the orchestration first, and then optimize and build the backend second. So that's why I made the backend trait. So it's pretty much a list of operation traits with associated types, like the device and the tensor data structures. And it's very unopinionated. So this is an example of a simple function, so an addition, and you see that they receive as parameter associated types for the float tensor types, and they return the same thing. So it allows backends to actually implement their own operations with their own data structure quite easily. But I also wanted to support training. So I made the AutoDiff backend decorator. So just, I'm going to say backend too much here. Sorry about that. But AutoDiff is a backend. It implements the backend traits. And it's also generic over another backend. So it's kind of a backend decorator pattern. And it just changes the behavior of flow tensor operations to calculate gradients during trainings. So it reuses the inner backend to calculate most of the gradients and the updates. So it means that you can do something like that. So declare the backend that you want to execute the operations, and then if you want to train a model on that backend, you can just wrap it with the AutoDiff backend decorator. So it makes any backend actually an inference backend and also a training backend. So the first version of Burn, I had only 3 backends. So ND array, which is a popular multi-dimensional array in Rust, so a fully Rust deep learning framework from the get-go. But also I had the libtorch backend. So libtorch is the C++ library behind PyTorch, and there were already existing bindings in Rust, so I used that. And obviously the AutoDiff backend that I just presented. So yeah, with the first release, I got around 700 GitHub stars. I had a small M.Sc training demo. You can go look actually at the Burn website. We have an inference M.Sc demo that you can look. It's just to recognize and classify digits. Back then, we only supported training. We didn't have any WASM inference engine, but now we do. So yeah, you can check it out. So yeah, the first release was quite good, and after a few weeks, I got a lot of people involved with the project, but it was not ready to be used widely. So I had to actually add a lot of different components. So more neural network modules, more optimizers, more features overall, and I did that with the help of the community. And with that, I think at that point, we had a production-ready prototype with Burn. So a lot of people used it for training and in production for their application. But I don't think it was the best option out there. I wanted something better. So I switched full-time. I raised a pre-seed round. I put in the company, and I partnered up with one of my friends from college, and we were going on an entrepreneurship adventure. So pretty happy about that. The plan was actually very clear. First, we will build the fastest deep learning framework without compromise on portability, and flexibility. Then we'll build a cloud platform to help users train and deploy their models. And finally, we'll have a successful business. That's great. However, point 1 is not very easy, though. That's quite hard. Today, we are between 1 and 2, let's say. Yeah, but it's progressing well. So let's go over the requirements, so if you want to pull that off. So what do you want to do? So those are all of the requirements you need for flexibility, performance, and portability. So you need dynamic graphs, you need dynamic shapes, you need kernel fusions, you need also to support specialized instructions like SIMD and tensor cores on NVIDIA GPUs. And if you don't want to write everything all the time for all of the different platforms, you need a translation layer, which is pretty much a compiler. So the problem with this is that fusion and dynamic graphs are pretty much incompatible. It's very hard to actually have both in the single project. So let's go over and see what dynamic graphs are before going further. So dynamic graphs, what it means is that tensor operations are simple function calls. So you install a library, you create a tensor, you run some operations on it, simple functions, easy. You are still in control of the execution flow of the program. You can do pretty much whatever you want. And dynamic shapes mean that you can actually have shapes of different size, similar to dynamic vector in Rust. So you can push and extend the tensor. So it's very useful for dynamic image with different resolution, dynamic sequence of text, and yeah, a lot of other stuff. The alternatives? Well, static graphs mean that tensor operations are not simple function calls, they are configurations. So you configure all of the tensor operations that you want to execute, and then you send them for execution to a runtime. So you lose control over the execution flow of the program. You cannot actually do a lot of debugging easily. And if you don't support dynamic shapes, you support static shapes, it means that you have to do masking. So if your model wants to support different image size, well, you have to define the worst case and then multiply by zeros the things that you don't want to calculate. So it's called masking. It's not fun, but sometimes it's good to do even if you have dynamic shapes, but it's not easy to work with all the time. So imagine if you did not have access to if statements, for loops, dynamic memory, print statements, etc. Well, programming will be hard and debugging will be painful. So why do static graphs exist? Mostly because of kernel fusion and performance reason. If the compiler or the runtime has all of the information about all of the tensor operations and allocations that are going to happen during execution, you can do a lot of optimization. So I'm going to go over what is fusion with a small example. So this is a laser, yeah, and this is the code snippet. It's a function that is doing pretty much nothing useful, but at least it fits on the screen, so that's why I used it. We have two tensors and two intermediate values, so temp1 and temp2, and we're doing multiplications and addition, nothing fancy. If we would unroll all of those tensor operations, it could look something like that. So this is a bit small, but if you look at the top of the code snippet here, you see that to calculate temp1, you need to allocate a new tensor, iterate over all of the values for x and y, store the result in the newly allocated tensors, and you return it. And that newly allocated tensors becomes the temp1 tensor. You do the same thing for temp2 and the same thing for the output. Well, with that, you have 3 allocations, 2 for temporary tensors, 1 for the output tensors. And if you look really carefully, you see that you read x and y 2 times each. So we can do better than that with kernel fusion. So with kernel fusion, it would look something like that. So we merge all of the for loops into one, and then we have only one allocation for the output here. And then we iterate over all of the same values. And the key benefit here is that the temporary values only exist in register space. So we save a lot of global reads, global writes, and a lot of allocations. It's way faster than the other implementation. I didn't really benchmark it because, time, but it's probably 3 to 5 times faster. So how do you manage to do it with dynamic shapes, with dynamic graphs, sorry? Well, with a lot of refactoring. And the key idea was to move away from functions that receive tensor with references to functions that receive own tensors. So what it allows us to do is to keep a reference count of how many times a tensor is used. Because if you want to use a tensor multiple times, because of the ownership rules of Rust, you have to clone it. And coupled with lazy execution, we're able to actually gather all of the information required to perform fusion. So the key idea here is that the information to perform those optimizations are not given by static configurations, but by the ownership rules at runtime. So thanks for the Rust type system. So where are we? Well, I just go over dynamic shapes, dynamic graphs, and kernel fusion. So right now, I'm going to go over the specialized instructions, like SIMD and tensor cores, and the compiler. So let's go back in time to the first version of our custom backend. So it's made with WGPU. So some of you probably know the crate. So it's the popular GPU crate behind the Bevy game engine, behind EGU, and the Cosmic desktop environment. So it's a very popular crate. So that's why we chose it. But the first version was pretty trivial. Though we didn't have any compiler, we used string templating with predefined algorithms. So very basic. We didn't have fusion either, because all of the tensor operations had their own templates that we would run. And we also didn't support specialized instructions, because WGPU and WebGPU is pretty much only 32 bits floating point operations. But at least it was multi-platform, because WebGPU can run everywhere, even on browser. So at least that's that. And we were quite slow. I would say 5 to 10 times slower than libtorch. But it was a beginning. And because of Rust, we were quickly able to refactor the whole code base and move away from string templating to a proper compiler IR. We were also able, because of that, to implement another target for the compiler IR. And we added a CUDA compiler and a CUDA runtime. But we created a monster along the way. So this is a code snippet that did something. I don't recall what. But it's like 4 multiplications, and it's huge. So it's kind of terrible, because we had to manually configure the compiler IR ourselves, manage variable declaration. We had macro at every line, because the builder pattern is even more verbose than that. It didn't scale. We were not able to build complex and performant algorithm with that tooling. So we went again. We refactored the whole code base. We already had the compiler IR. What we were missing is actually a pretty front-end syntax. And we liked Rust, so we stole it. We stole the Rust syntax using procedural macros. So the process is pretty simple. We use the syncrate to parse the Rust code. And then we generate the compiler IR. And finally, we send it for execution to a runtime, like the CUDA runtime or the WGPU runtime. Rust is fantastic. It's crazy that we can do that. And just to clarify, all of those refactoring were between Burn releases. So all of those things actually shipped to production. They were, like I said, production-ready prototypes. People use those backends. And we can iteratively improve all of our systems and internals. But because it was becoming quite a bigger project, we call it CubeCL. So it's a Rust compute project. So this is a code snippet of CubeCL. You see that you only have to annotate a code, Rust code, with the cube annotation. And we support a lot of Rust syntax. Not all of it, but a lot of it. So we support generic, we support traits implementations, we support associated types, we support functions, reference, mutable reference, and match statement. And something that we kind of discovered along the way, because of how we do the compilation process, is that we could leverage compile time, comp time, that's how I call it. You can call any Rust function during the just-in-time compilation process of a GPU kernel. So that's really helpful to build a lot of optimized code. So in this case, the match statement will not actually produce a branching on the GPU code, because it's going to execute during the just-in-time compilation process of the GPU kernel. So we use it a lot. It's very convenient. It's similar to Ziggs, but it's in Rust. So CubeCL is multi-platform by design. So today we support CUDA, ROCm for AMD GPUs, Vulkan for pretty much any GPUs, web GPUs, like I said at the beginning, Metal for Apple, and finally we also added a new LLVM backend. So LLVM is mostly to target CPU right now by supporting a lot of SIMD instructions. So in a way, we kind of implemented a new Rust compilers for numerical computing with CubeCL. So where are we? We went through all of the requirements. So dynamic graphs, dynamic shapes, kernel fusion, specialized instructions, and the compiler stacks. So now where are we? Well, we need to do a bit more optimizations regarding our algorithm. So we have a state-of-the-art matrix multiplication kernel engine built on CubeCL, but we're still missing some of optimized instructions that we could support, like the newer NVIDIA Tensor Cores, FP4, FP8, and we're working on it. Same thing for convolution. We're also working on flash attention, which is a very important kernel for LLM inference and LLM training. Same thing for quantization, which should land in the next release of Burn. So as summary, we just need to build the ecosystem. So it's not going to be built overnight, but we're working on it, and it's fun to do. So yeah. And we made a platform, which is called the Burn Community Benchmarks, so to keep track of performance optimization that we're making. So you can actually clone a repo on GitHub and run all of the benchmarks on your own hardware with different backends. And you can share the results with us anonymously, and then we can compare with different backends, different hardware, different Burn versions. So it's really our way to measure the progress of Burn in terms of performance. So we're also working on Burn-LM. So Burn-LM is a new project that aims at democratizing large model inference and training on any device. So the strategy is pretty simple. We're going to provide strong open source model implementations, and we're going to funnel back all of the optimization that we're making in Burn and CubeCL. So we don't want Burn-LM to be a collection of custom optimizations for LLM. We want to generalize those optimizations and bring them directly in Burn and CubeCL, so that anyone building models with Burn would benefit from those optimizations, not just the one using Burn-LM. And it's also our way to prioritize features and optimizations, because we have a lot of work, and sometimes it's hard to prioritize what to do. In conclusion, Burn and CubeCL wasn't made overnight. It's an evolving system. It's a production-ready prototype, and it wouldn't be possible without traits, enums, associated types, the ownership rules, procedural macros, and a lot of Rust features. It wouldn't be possible without Rust. So I'm really glad I chose Rust when I started that project. And today, with Rust, you can actually train and deploy models with Burn. And there are other projects out there like Kernel and some other frameworks. So the ecosystem is getting there. And if you want to do it with Burn, we have a lot of learning resources. So we have the Burn book. It's over 100 pages. We have the CubeCL book, which is, well, it's a work in progress. It could be better, but it's going to get better. If you don't find the information that you need, you can join the Discord channel. We have a lot of people there, and you can ask your question. We're going to answer them. And during the talk, I went pretty light on the technical details. But if you're interested into how we actually build Fusion, how we actually build the Matmul kernel engines, we have technical blog posts that you can go and read them. So yeah, feel free to do that. And I really believe that Rust could become a major language for AI just because of all of the type systems and all of the properties that the language has. And not just for AI, but also for accelerated computing. Because now today, you can program any GPU and CPU using Rust, and not just with Burn and CubeCL, but like I said, with other projects like Rust GPUs, with Kernel, and a lot of other crates. So I really believe that Rust could become a major language in high-performance computing. Thank you.